Well, so in this lecture we will continue with the tableau procedure for model checking of LTL properties, and then we will look into CTL model checking. So, to recall what we did in the last lecture, our strategy for model checking LTL properties is that we extract out a state machine from the implementation, we create a tableau or an automaton from the property, from the negation of the property, and then we check the emptiness of the language which is at the intersection of the language accepted by the automaton and the implementation. Now, remember that the acceptance criteria is the Buki acceptance criteria, that is accepting states must be visited infinitely often. So, at least one of the accepting states must be visited infinitely often. So, to check that part of the thing, we first need to compute the strongly connected components in the product of the two machines. What do we mean by a strongly connected component? It is a set of states such that from each of those states you can reach each of the other states. Okay, so, then that is called a strongly connected component. So, a strongly connected component obviously can exist only when there are cycles in it, right. So, that from every state you can visit every other state in that component. Now, for a large state space, finding out the strongly connected components is a non-trivial problem. Okay. But not only do we need strongly connected components, we need strongly connected components containing an accepting state, because if there is a strongly connected component having an accepting state, that means that we can go stay in that strongly connected component and visit the accepting state infinitely often. So, that means that there will exist some path which is accepting for the product automaton. But if we do not have any such path which visits an accepting state infinitely often, then which means that the product does not have any sequence which is accepted by the automaton for not of var phi, which means that the property var phi has been proven, because there is no counter example trace for it. There is no trace which satisfies not of var phi. Okay. So, this is what I said just now, that the product of the two machines is a Buki automaton, again because the acceptance criteria is still the same. How do we find accepting sequences? Accepted sequences must contain a cycle, otherwise how can we visit the same state infinitely often? So, we are interested only in cycles that contain at least an accepting state, and during depth first search what we can do is we can start a second search when we are in an accepting state. Okay. I will explain this in more details, but this is the most naive algorithm for finding out the accepting runs in your product automaton. Okay. But later on we will see there are better methods of doing it. So, let us see what this means, that we start with the original state space and do a depth first search. Okay. So, we traverse this state space depth first, then after this we come back from here and then try this, okay. Then we come here and now we have hit upon an accepting state. Now, what we must see is whether there is a cycle by which we can come back to this accepting state. If there is such a cycle, then we have found a accepting trace, right, because what we can do is we can start from the starting state here, come along this path and then traverse in that loop, okay, if there is a loop containing this state. So, what we do is when we reach this accepting state, we start a second DFS starting from here. So, this is the second DFS. Now, when we have reached the same state again, now we know that this path is the accepting path. or the accepting trace, infinite path going infinitely often through this accepting state. Okay. So, this is a very trivial algorithm for doing it, and the algorithm pseudocode is given here. So, what we do is, this is the initial DFS that we start at from the starting state. So, we keep an array called visited, and with that set we augment every node which is visited. Then for each successor S dash of S, if S dash is not visited, then we must visit S first. So, we recursively call DFS with S dash, and if S dash is an accepting state, then we call the second DFS, that is we call DFS 2 with S dash as the starting state and with S dash again as the target state, right. So, what does that mean? We will see in the next slide. Okay. Now, what is DFS 2? DFS 2 does the following thing, that for each successor S dash of S, if S dash is equal to the second parameter, then it says that I have detected a cycle, and otherwise if S dash is not visited, then it proceeds exactly as in DFS, right. So, it is exactly a second DFS, except that we keep on matching with the second parameter. The second parameter is the accepting state. So, if we hit upon the accepting state during this DFS 2, then we return cycle detect, otherwise we continue as in the normal DFS. Is that clear? Now, we will go into CTL model checking right now, but what we are going to do is, after studying CTL model checking, we will come back and show that there is a better way to handle large state spaces and solve the same problem in using CTL model checking. Okay. So, let us see what CTL model checking is about. So, recall that the difference between LTL and CTL is mainly that in CTL every temporal operator like x, until or always has to be immediately preceded by a E or an A, right. So, we do not allow things like GFP. GFP is not allowed. This is LTL, but not CTL. In CTL, we have to prefix each of these temporal operators with an A or E. So, for example, AGEFP is okay, it is in CTL, right, or AGAFP is CTL, and so on, right. Now, we will see that this requirement, that every temporal operator has to be immediately preceded by a quantifier like E or A, actually helps us in performing CTL model checking in a dynamic programming like approach. So, I will explain that in due course of time. So, the basic modalities that are required in CTL are EX, EU and EG, and all others can be expressed in terms of these. For example, AFP can be expressed as not EG, not P. Okay. AGP can be expressed as not EF, not P, and AP until Q can be expressed like this. This is slightly more complicated. What this says is that if you want A P until Q, which means that along all paths P until Q must hold, right, then we need to have that not EG not Q, which means that along all paths in future Q must hold. What does this thing mean? Just let me choose a. What does this thing mean? This is the same as AFQ. So, it says that along all paths in future Q must hold. So, AP until Q requires that along all paths Q must hold in the future, and what does this say? It says that not Q must hold until this part says there exists a path where not Q holds until not P and not Q holds, right. So, what does this mean? What does this mean? In what ways can the P until Q property be refuted? One is that Q is not true anywhere in the future. So, that is overruled by this, that Q must hold in future. The other way that it may not hold is that you have a path where you have P and not Q, and then you somewhere down the line, before you get the Q, you get a not P and not Q. Okay. Then even if you have Q somewhere down here, see the P until Q does not hold, because in intermediate state P is not holding, right. So, this one actually says that that is not going to happen, alright. So, this part says that it will not be the case that you get a not P not Q situation before you get the Q. Okay. Now, let us see how we go about doing CTL model checking. So, the first thing that we need to understand is the computation of a reverse image, right. So, the idea is that if I give you a set of states S, right, and I give you the transition relation R, S S dash. What is S? Present state, S dash next state. Now, remember that we saw that if you have a design which has both inputs and outputs, then we can transform it to a non-deterministic transition system where you only have state bits, right. I mean, the input bits are also treated as state bits, remember, and then the relation becomes non-deterministic. So, assume that this is such a relation, that we have only S and S dash is the present state, S is the present state, S dash is the next state. Now, given a set of states S, how can we find out the set of states which is the set of next states of these states, right. So, in other words, we are interested in finding out those states from which are next states of some states of these, right. So, to get that set of next states, what we can do is that we can say that okay, let us do S, this set S, okay, intersection R S S dash. Okay. So, let us say this is the set of present state X and we take R S S dash, right. Now, see what we can do is we can represent S by a function, Boolean function. Why? Because these, what are these state bits represented by? They are represented by Boolean vectors. Okay. Why? Because every state is some 1 0 1 1 0 1 1 0, it is some encoding. Okay. Now, what you can do is for any set of states, you can define a function which gives you 1 whenever one of the elements of the state is of the set is presented, and suppose the state 0 0 0 1 does not belong here, say 0 0 0 1 is outside this set, then corresponding to that this f will be 0, right. If we define it like this, then this function represents this set. Okay. So, any set of Boolean numbers, any set of binary numbers can be represented by a function. Okay. Now, suppose PS is that function corresponding to this set of states, right, and RSS dash is the transition function. What is a transition function? Remember that we saw when we were looking at BDDs that you can create transition functions also as Boolean functions. How? Suppose you have a state 0 0 0 1 and from there you have a transition to 1 1 0 0, right. Then in the transition relation we will say 0 0 0 1, then 1 1 0 0, and then the corresponding value of R is 1 here, because this transition exists. On the other hand, if there is no transition from 1 1 0 0 to 0 0 0 1, then we will have 1 1 0 0 to 0 0 0 1, and this is going to be 0, right. So, this is the transition relation expressed as a function. Okay. So, we can represent the transition relation as a Boolean function, we can represent the set also as a Boolean function, and then when you compute the intersection of these two, what is it going to produce? It is going to produce, it is going to actually find out those valuations of S and S dash for which this is true and PS is true, right. So, that means that it is going to pick up only those transitions in which the S belongs to this, right. So, it is going to find out all transitions which come out of this state, this set, okay, right. Now, from that set of, so from that set of vectors, if we only choose the S dash part, then what are we going to get? We are going to get the set of next states of S, right. So, if we say that, if we define this set, there exists S dash, okay, such that PS intersection R S S dash. This represents the set of next states of the set S, right. Now, see what will we do if we do this using a BDD? We will create a BDD corresponding to PS, we will create a BDD corresponding to R, okay. The set of variables in this BDD will be S, the set of variables in this BDD will be S plus S dash. Now, then we will do a BDD AND of these two. Now, what will be the set of variables in the ANDed BDD? S union S dash, that will be the set of variables, right. So, in the in the product BDD, you will have a BDD where along the paths that lead to 1, you will have transitions where S belongs to this and S dash is something, right. From this BDD, if we restrict out these variables or eliminate these variables, we will be left with this, right. So, by that way we are able to compute the set of next states of the set of states, and in a BDD this is going to be one single operation, one operation for this AND and one operation for computing this restriction, okay. So, with two BDD operations you will find the entire set of next states of this set of states, clear. Now, how do we compute the pre-image? So, this is the image of S, the set of next states of S, right. Now, by using this we can compute the set of reachable states. How? What we do is that we start like this. We say that Z0 is the initial set of states. So, that is equal to S, right. Then how do we compute Z1? We compute Z1 as Z0 union there exists S dash P right. All right. There is only one thing that I skipped here. See, these variables will be S dashed. So, we need to rename them to S before taking this union. Okay. So, if you had variables, the present state variables are S0, S1 through Sk, and the next state variables are S0 dash, S1 dash to Sk dash. Then after performing this restriction, we will be left with only this set of variables, right. But in order to take union with Z0, we must rename S0 to S0 dash to S0, S1 dash to S1 and Sk dash to Sk, right, because they are the same set of states. Now, this, what does this Z1 gives us? The Z1 gives us that if we start with S, then Z1 is S union the set of next states of S, right. Then we define Z2 as Z1 union so what does that give us? So, this whole thing was our Z1. Then we compute the next state of Z1 and union with Z1. So, this is our Z2. Okay. This was our Z0, this was Z0, this is Z1, this is Z2, right. In this way we continue until we reach some Zi which is equal to Zi minus 1. Now, when this happens, that means that there are no new reachable states. This is the fixed point. Now, because we are dealing with a finite state machine, this fixed point will always exist, right. So, we are growing the set of reachable states in every iteration by computing the image, and then finally, we reach some stage, we will always reach some stage where in successive iterations the set does not grow anymore. So, when you have reached the reachable set of states, if you again compute their successors will also belong within that state set only. So, we will not go any further, that is the fixed point, and then we have found out the entire set of reachable states. Okay. How many iterations will we require for this to reach the fixed point? The diameter of the graph, the diameter of the state transition relation. Whenever we reach the diameter of that, beyond that obviously by that time we have already covered the entire reachable state. Okay. Now, let us look at the pre-image computation, and I will explain why we will need the pre-image computation in a moment, but what we mean by a pre-image computation is that I start with S0 and then I want the set of states from for which the that there is some next state in S0. I want the set of states which have some successor in S0. Okay. So, this is the pre-image. Okay. Now, how do we compute the pre-image? So, I am given P of S0. This is the function representing the set of states in S0, and I am given the transition relation R S S dash, which is S, and I am given R S S dash. So, I want to compute the predecessor states. So, to do that, let us do the following thing, that we rename the variables here from S to S dash. So, this is renamed to P S dash. What is this renaming? Again, just let me reiterate that if this had variables S0, S1 through Sk, we just rename S0 to S0 dash, S1 to S1 dash, and Sk to Sk dash. Okay. We rename this. Now, if we take the renamed this thing function and take its intersection with RSS dash, what is this going to have? This is going to have only those transitions for which S dash is the next state, right. So, in the product BDD, if we do it with BDDs, any path which reaches a 1, which is the 1 node, will be such that the S dash valuation is one which satisfies this one, right. So, the next state belongs to this, right. Now, if we put a there exists S before this, then this captures the set of states which are predecessors of this set of states, right. So, just like we did the post image computation, where we used S here and we said there exists S dash, we just do the reverse, right. And from a functional point of view, there is no difference between these two. So, this computes the pre-image. Okay. Now, again, if we apply the same style of reasoning, that we start with Z0 as S, okay, and then we say Z1 is Z0 union there exists S P Z0 and RSS dash, then this is essentially computing the pre-image of Z0, and we can do it like that in a similar way until we reach some state where Zi is the same as Zi minus 1. So, then we have computed the entire set of states from which these states can be reached. What does the final Zi give us? It gives us the set of states from which a state in S0 can be reached, right. Is this part clear? So, now let us come to this thing here. This is what this says, that if you have a set of states P, then image inverse PR, where R is the transition relation, is this set of states, okay, which is a pre-image, and we can compute it by saying that okay. Now, suppose we want to compute EXP. What does EXP means? That suppose I give you the set of states which satisfy P. If I give you the set of states which satisfy P, then how can we compute EXP? It is the set of states which are predecessors of this set of states, or in other words we are looking for the set of states for which at least one next state belongs to the set of states which satisfies P. Okay. So, given the set of states which satisfies P, we want to compute the pre-image, and that pre-image is the set of states which satisfies exp. So, exp is therefore there exists V dash belongs to R and P belongs to this should be L V dash. Okay, this is a typo here. This should be L V dash. There is a typo here. This should be L V dash. Okay. So, there exists V dash belongs to R and V dash satisfies P, which means that P belongs to L V dash. L is the leveling function of the Kripke structure, okay, which says that which propositions are true in which states of the Kripke structure, right. Now, how do you find out the set of states satisfying P? So, P is a proposition. Now, think of the actual state machine. Okay. P is a label. What is a label? It is an output, right. So, suppose that at this point of time the state bits are S0 through Sk. What is P? P is some function of S0 through Sk, right. Why? Because output is what? Output is a function of the state, right. So, that is P. So, P is not specified explicitly as a label in the sense that you do not enumerate the set of states in which P holds. Rather, P is specified as a function over the state bits, and whichever state valuation makes this function 1, the output P is 1 in those of this case. That is because you see in a finite state machine, okay, there is some logic function here at the output which produces the output P. Given the states, there is some logic function which takes the state bits as the input and produces the output, right. So, that is how P is specified. Now, the BDD corresponding to this F is actually the set of states which satisfies P, okay, or this function represents the set of states which satisfies P, right. So, that is how we start with the set of states which satisfies P, and then we take the function corresponding to the transition relation and compute the pre-image to get the set of states exp, right. Is this part clear? Okay. How do we compute EFG? Now, instead of EXP, we now have EFG. So, in the future, G must hold. So, what we do is we start with the set of states which satisfies G. Okay. Now, note that G could be some formula, but we somehow are able to compute the set of states which satisfies G. Now, given the set of states which satisfy G, let us see how we can compute the set of states which satisfies EFG. So, we can rewrite EFG, as the set of states E sorry, this will be either G or EXG or that is how we can write EFG, right. So, what we will do therefore is we start with the set of states which satisfy G. This gives us G or EXG, the pre-image. We compute the pre-image of that set. So, this set of states satisfies G or EXG, right. Then compute the pre-image of that gives us G or EXG or EXG, right. Is that clear? And in this way we continue until we reach a fixed point. Okay. Now we call it a least fixed point. Why do we call it a least fixed point? Let us see, is the size of these growing or shrinking? It is growing, right? It is growing. So, at some point of time when we reach a fixed point, that set has a set of states, right. It has some set of states. If I add some more states into it, right, then also it is going to contain all the states which satisfies EFG, but those additional states. So, we keep on growing this until we reach the fixed point, okay, and then there can be other fixed points which are larger than that, right, but not derived out of this. What fixed point are we trying to reach? The set of states and their predecessors are all contained in it. So, there is no other state that you can reach by backward reachability, right. So, this is one component, right. If I take another component and also put it in this, it may still satisfy the same fixed point property, that no new states are added by reverse image computation. But what we are interested in is exactly this minimal set. Why? Because this is the set which satisfies EFG for me. Okay. So, we call it the least fixed point. It is the first fixed point that you hit as you go backwards, right. And similarly, we will see that we will need a greatest fixed point for another type of properties. So, is the procedure clear? We start with the set of states satisfying G, do a reverse image computation to find the states satisfying G or EXG, then do another reverse image computation and continue in this way until we reach the least fixed point. That set of states represents the set of states which satisfies EFG. Clear? So, this is the procedure, check EF, where SG is the set of states satisfying G in M. So, we start with the empty set, with Q as the empty set and Q dash as SG. While Q not equal to Q dash, okay, so this is the check for the fixed point. We do Q equal to Q dash and then Q dash is recomputed as Q union the reverse image. Okay, this is the reverse image, and we take the union of that with the present set which is Q. Okay. Now, this Q dash is therefore the next circle that we saw there. Okay. And we go around doing this until in some iteration we find that Q and Q dash are identical. That is where we have reached the fixed point, and fixed point we must reach because this is a finite state machine. And then we say that SF is equal to Q and we return SF, which is the set of states which satisfies EFG. Okay. So, it is an, if you use BDDs, this is a very small piece of code, just one BDD operation here, out here. Now, let us come to EFG, rather EGG. Okay. This says that there exists some path where G must hold globally. Okay. So, let us say that, let us start with the set of states which satisfies G again. Now, you tell me one thing, that if I give you the set of states satisfying G, all the states which satisfies EGG will be a subset of this set, because if there is a state which satisfies EGG, then it will also have to satisfy G. What does EGG say? That there exists some path where globally G holds. If there is such a path, then in this state also G will have to hold. So, the set of states satisfying EGG is a subset of the set of states satisfying G, right. But every state satisfying G does not satisfy EGG, because G may hold here, but all my next states may not have G, right. It may be the case that G holds in this state, but the next states do not have G. So, then EGG will not hold. So, if we start with the set of states satisfying G, we know that some subset within this is our EGG. Okay. So, what are we going to do? We will first compute the set of states corresponding to G and EXG, right. How do we compute EXG? Take the set of states G, compute their pre-image, that gives you the set of states corresponding to EXG, take the intersection of that pre-image with G, with the set of states satisfying G. Now, that is going to be a subset of this, obviously, because G is here. So, every state in this set will have to satisfy G. So, it is contained within the set of states having G. Moreover, it has to have a next state which satisfies G. So, this is a subset of this, right. Then in the next iteration, we take this and then compute G and EX of this set of states, right. So, if I call this Z0, then this is Z1. Now, see, in Z1, when computing Z1, I am using Z0 here, okay. And now this is my Z1, and what I am computing here is Z2, right. And in this way I continue until in some iteration Zi will be equal to Zi minus 1, right. And that set of states will be the set of states which satisfies EGG. And this will be the greatest fixed point. Okay, because it will have the most number of states among the points. Clear? Is it clear how we did EFG and EGG? There is a difference between the two. In one we compute the least fixed point, the other we compute the greatest fixed point. This is the pseudocode of the algorithm. So, given a model M and SG, the set of states satisfying G in M, this is the procedure which checks EGG. So, Q is S, Q dash is SG, while Q not equal to Q dash, here instead of taking the union we take the intersection, and this is again the pre-image computation. Okay. And we go on doing this until the states grow smaller, 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 and finally we reach an intersection. Right. Now suppose the property is not satisfied, in the sense that there is no state which satisfies EGG, then where is this going to terminate? It will terminate with the null set. In two successive iterations you will find that q equal to q dash, because both are null. Okay. Now how do we check larger CTL formulas? So we have seen the basic properties how we check them. Okay. We did not talk about p until q. How are we going to compute p until q? Let us quickly see that. We will start with the set of states satisfying q. So start with the set of states which satisfy q, right? Then compute their pre-image, right? Pre-image of this is what? Ex q, right? So we are looking at EP until q. All right. Out of this, which ones do we want? The ones which satisfy P, right? So intersection P. Okay. So this is our, we call this our Z0. This is our Z1, right? Now let us work one iteration backwards. And with
P or Q instead of P.
No, we are going to take the union of this with this. Z1 is this union Z0. Z1 is this union Z0, this whole thing. Okay. So all those states which satisfy Q are already in this. Okay. Then the next one is that if you have this set of states, then basically what we need is we need Ex Z1 and intersection of P with them, right? Union this whole stuff. So that is our Z2, right? And we go on in this way until we reach a fixed point, right? So what are we, in each step what are we computing? Z0 is Q, Z1 is Z0 union all those states which satisfies P and Ex Z0, right? It has to have a next state in Z0 and it has to satisfy P. Z2 is Z1 union P and Ex Z1. Right. So when we have this, then we have the set of states which satisfies EP until Q. Right. We haven't yet talked about how we tackle properties which have A. Right. So the idea is that if you want to find out a set of the set of states satisfying AFQ, right, what we do is we rewrite this as not EG not Q, right. Then what do? We start with the set of states which has not Q, right. In fact, this is going to be that we start with the set of states not Q and then reduce it progressively until you reach the set of states, the fixed point, which gives you the set of states EG not Q, right. Now, given this set of states, how do you find out the set of states which is the not of this? Just complement it, okay. So, the once you have this set of states, the complement set of states is the set of states which satisfies AFQ, right. So, all A formulas will be treated like that. We will first negate them, get it into E form, use this reachability analysis to find the set of states satisfying the E formulas, take their complement to find out the A formula. So, you see it is very systematically done, all right. So, what we will next see, and we are running out of time in this lecture, is that how do we take nested CTL formulas and check them using the procedures for these basic CTL formulas. Okay. We will discuss that in the next lecture.